So let us continue with some more basic algorithms. Okay. So this time, let's try to compute the solutions of a quadratic equation. Remember quadratic equation, right? So solutions of a quadratic equation. So write an algorithm to compute the solutions of roots of a quadratic equation. Okay, solutions of a quadratic equation. But you need to specify how it is mentioned, right? Because depending on the type, the algorithm might change a little bit. So where the equation is given as ax squared plus bx plus c equal to 0. Okay, this is the format in which the equation is to be taken. It is to be input. All right. So how does this work? So what do we do? So we assume that the equation ax squared plus bx plus c equal to 0. In order to know this equation, what do you need to know? You need to know the coefficients a, b, and c, right? So we'll assume that this equation is passed as an input of, coefficients a, b, c. Okay. If I give you this 3-length vector a, b, and c, then you know what the equation is, right? All right. So let's write that. So solve. Okay. So that's the name I'm giving for the algorithm. The inputs are a, b, and c. What is the output supposed to be? Output is supposed to be the set of roots. If there are repeated roots, then you show the root 2 times. Okay, you show the same root 2 times. Is that all right? What is the first thing to check? In this case, the equation is very easy. So let's check the values of a, b, and c whenever they are zeros, what it gives, right? So first of all, if a is equal to 0, then it's a linear equation. Is that right? It's a linear equation provided b is non-zero. Suppose b is also 0. Okay, then let's check. If b is equal to 0, then c must be 0. Isn't that right? In that case, c must be 0 because a and b are both 0. But suppose if you give c non-zero as the input, then it should say that the equation is incorrect or equation is inconsistent, right? So you're supposed to give if c is not equal to 0. In this case, a 0, b 0, but c not equal to 0. Then you need to give an error that the equation is not consistent, or let's say not correct. That's enough. It cannot be, right? Because 0 plus 0 plus c cannot be equal to 0 when c is non-zero, right? Else, what happens here? If c is equal to 0, a is 0, b is 0, c is 0. Then it just means c 0 is equal to 0. So what are the solutions? Every real number, or rather every complex number, roots can be complex numbers also. So every complex number is a solution. Isn't that right? So we'll give the message. Let's say, so we are printing the message in this case. Okay, so let me introduce a new command, print. Print simply says whatever is written later on, that is printed. Okay, so print. So what do we print? The text. Solution set is equal to, let's write the usual notation. Okay, z equal to whatever x plus iy, where x and y are real numbers, right? Every complex number will be a solution. So this is our solution set. Is that okay? This completes this if. Alright. So we come back here. In this case, so now it's the else part of this. What does that mean? B is not 0. When B is not 0, it's a linear equation because A is already 0. We are still inside this case. A is 0, but B is not 0. So it's a linear equation Bx plus C. So the solution is minus C by B, right? X is equal to minus C by B. So again, we'll just print solution set. This time it's a single value, right? So minus B by C. It's a single value, you see? I'm sorry, minus C by B. Very sorry. Minus C by B. X is equal to minus C by B. The equation is Bx plus C. Okay, that's the solution. And this completes this end. Now when you come back here, what do you get? Else. Now we are in business, right? A is not 0. So now this is properly a quadratic equation. It's not a linear equation. It's a quadratic equation. What is the first thing you do? Compute the discriminant, right? So let's say D is a discriminant. What is the discriminant? B squared minus 4 into A into C, right? B square minus 4AC. Remember? Compute this. Okay. So when do you have real roots? When B square minus 4AC is greater than or equal to 0. So that's the two cases you have. So if D is greater than or equal to 0, which means the discriminant is greater than or equal to 0, right? What is the formula? Just print out the formula, right? So print solution set is equal to, what are the formulas? So now you can just think about it. So minus B plus, let me just write square root D, right? Because it's B square minus 4AC divided by 2 into A, again in bracket. You understand the bracketing, right? So minus B plus square root D is the numerator, 2 times A is the denominator. This is the first value. Second one is the negative, right? So minus B minus square root D divided by 2 times A, that is the second root. Okay, so these are the two roots of this equation. These could be equal. When D is equal to 0, you have repeated roots, so this might evaluate to the same number. That is all right. We don't care about that. Okay. Second thing is, if this is not true, so else part, what is the else part? The else part comes when D, the discriminant, is less than 0, right? When discriminant is less than 0, what does that mean? You have a square root minus 1 coming up, right? So now just check again, the I, the imaginary part I can be written as square root of minus D times I. Okay, because D is negative. So you have square root D as an imaginary number. It's something times I. So it's square root of minus D times I. Okay, so just check that, right? So in this case, the solution set is equal to, very similar to the previous one, minus B plus, it's going to be square root D, sorry, square root minus D, okay, square root of minus D, because minus D is greater than 0 here, times I, the imaginary component. Square root minus D times I. You understand? This is the square root minus D is the imaginary part, right? Divided by 2 times A as before. And then the second root is again minus B minus square root of minus D times I divided by 2 times 8. Okay, so it's getting longer, so I'll just adjust some spaces to make sure it comes in one line. Okay, so this is what it is. This is the solution of the solution set in this case, and it's complete, right? We have printed the solution in all possible cases. So this completes the algorithm. And if that is for the discriminant, and then that's it, because the answers were only depending on the discriminant. So we have also covered completely the case where a is not equal to 0. So end it. Okay, so that completes the algorithm. Okay, and one main thing that I forgot, which is start and stop. Okay, so this is the algorithm for computing the roots of a quadratic equation, solutions for quadratic equation. Okay, just go through this once again and check that is correct, especially the part when the discriminant is less than 0, the else part. Check that the solution is actually this square root of minus d times I will be the imaginary part. Okay, so just check that. So that is it. All right. So what is the next thing to try? Let's try one more simple question. A very, very simple question this time. Okay, most of you can guess what it's supposed to be. Write an algorithm to determine whether a given year, calendar year, yeah, a given calendar year is a leap year or not. Okay, very, very easy, right? All of us know how to calculate a leap year. You would say that if the year as an integer, if it is divisible by 4, then it is a leap year, right? Not all the time, actually. There is a small exception case. There is a very small exception case which comes when you have years like 2000, 2100, 2200, or 1900, 1800, things like that. Usually, when the year is divisible by 4, it is a leap year. But in the special case, when the year is divisible by 100, okay, so these are called century years. 1900, 1600, 1500, 1200, 300, 2800, right? So whenever you have a century year, when the year is divisible by 100, it is not enough for the year to be divisible by 4. It should be divisible by 400. Okay, that is a rule for leap year. So in case you are not convinced, just do a Google search for leap year's definition and you will come to know this is a small exception. Okay, so we'll incorporate that in our algorithm. So let's write the algorithm. Now it's very, very easy, right? Leap year. The input is an integer which we'll call year itself. Okay. Okay. So start, stop. So now shall I do this? I have explained what it is. This is a very, very simple algorithm. Okay. So the answer is going to be either true or false as we have done before. So let me just write the algorithm and you follow it and see if you understand. In between, I will not speak. Okay. So what are we doing here? We'll first check that exception case. When it is divisible by 100, we'll handle that. And then we'll consider the usual case. Is that okay? So if, I hope you all remember what modulus means. You divide by the number and the remainder. Okay. All right. So this is the very simple algorithm to compute a leap year. Okay, just go through this once again and check that everything is fine and this makes sense to you. Is that okay? Right. So let's do one more algorithm. It's a very simple one once again, which is write an algorithm that prints the reverse of any positive integer. Okay? Prints the digits, let's call it digits in the reverse of any positive integer. Okay, what does that mean? For example, if input is 27884, then output is 48872. Is that okay? The number that you get by reversing the digits. Is that all right? So how do we do this? We are basically supposed to extract the digits and then reverse them, right? Right? So extracting the digit, do you now see the hint is the following. When you divide this number by 10, 27884, when you divide it by 10, the remainder is 4. When you divide it by 100, the remainder is 84. When you divide it by 1000, the remainder is 884. All right. So this is what you're supposed to keep doing. Okay. So let me write reverse number. The number is n. So first special case, if the number is 0, then you just don't do anything. Okay. So if n equal to 0, error. Well, not error really. I mean, the reverse is just itself. Okay. So just return 0. Else, this is where we start. Okay. So what do you do? How do you extract the digits? Okay. So note this. What we are going to do is we will remove a digit, that is the digit 4, then we will subtract it. Then we will get 27880. Right? 27880, when we subtract it, when we divide it by 10, we get 2788. Okay. So the idea is remove the last digit, then divide by 10. Then the next to last digit becomes the last digit. Then again remove the last digit and then again divide by 10. You understand? So, okay. So before we go to the algorithm, let's just run a trial run of this. So input, or rather n is equal to 27884. What I'm going to do is, let's say r is equal to n mod 10, which is equal to 4. Okay, so I will initialize two parameters. So this is the value which is 0, which is the reverse value. Okay, this is the remainder. Okay, all right. And now I say another index I is equal to 0. Okay, so value is equal to 0, I is equal to 0, and now I start. First step, remainder is n by 10 equal to 4. Is that okay? Then I do value is equal to value plus 4 into 10 to the I. Is that okay? Value is equal to value plus 4 into 10 to the I. 4 was the last digit. So rem into I. Sorry. Rem into 10 to the I. What does this mean? The remainder is 4. I is equal to 0. So 10 to the I is 1. 1 into 4 is 1. Value was 0. So this value is 4. Okay. And then I'll say I is equal to I plus 1. I'll do that. Okay. So then I becomes 1 now. Right. Next, what will I do? I'll do n is equal to n by 10, which now, sorry, n is equal to n minus rem by 10. Okay. N minus rem was 27880 divided by 10. Now n becomes 2788. Okay. Note this. Now we are going to go on repeating this. Okay. This was the first cycle. Now look at the second cycle. I'm going to repeat the same steps. Now I'll say rem is equal to n mod 10. What is that equal to? The value of n now is 2788. So mod 10 is going to give me 8. Then I say val is equal to val plus rem into 10 to the I. But now I is equal to 1. So 10 to the I is 10. So rem into 10 to the I is 80. And value was 4. So 80 plus 4 is, oh, I'm so sorry. Oh, I'm so sorry. There was a small mistake. The small mistake is the following. Very, very small mistake. Value into 10 to the I plus rem. Very sorry about that. Right. Right. Okay. So let's repeat this. So anyways, the first case doesn't really matter. So I is equal to 0, 10, 10 to the I is 1, 1 into 0 is 0 plus remainder was 4, so this is 4. Okay. I changes to I plus 1. N is n minus rem by 10, 2788, that's fine. Then we take rem is equal to, we now repeat this sequence of steps. Okay. Rem is equal to n mod 10, but n is 2788, so you get 8, last digit. Value is equal to value into 10 to the 8. Okay. Current value is 4, but I is equal to 1. So 10 to the I is 10. 10 into 4, 40. 40 plus rem, 48. Right? It's 48. Then I say I is equal to I plus 2. Sorry, I plus 1. But I was earlier 1. So now it becomes 2. Right? And then I say n is equal to n minus rem by 10, which is equal to now 2788 minus 8, 2780 divided by 10, 278. This completes the second cycle. Okay. Again, rem is equal to n mod 10. Now n is 278. So mod 10 is going to give me last digit 8. Right? Val is equal to val into 10 to the I plus rem. But note, what is I now? I is 2. So 10 to the I, 10 square is 100. 100 into value. Oh, sorry. Once again, this is small mistake. I just need to do into 10 into 10. Isn't that right? Uh, Okay, so let me just check this algorithm. Sorry about this. I'll repeat this part in the next video. Okay, let's just momentarily stop it. Okay, so sorry about the small mistake. So let us repeat this once again. Okay, so anyways, we have not written the main code here. So before that, let's do the trial run. Let's see how this is supposed to be done. So we have to reverse the digits of n. N in this case is 27884. So I'll initialize two variables, value which is 0 and I is equal to 0. Okay, and it turns out that we don't need I. Okay, so just value. Now rem will always extract the last digit. So rem is equal to n mod 10, which is the last digit. Then value, I will set it to value times 10. There's no I. Okay, value times 10 plus remainder. Value currently is 0. So I multiplied by 10, I'll again get 0. And then I'll add remainder, that's 4. And then we don't have this I equal to I plus 1 business, just this much. Then n is equal to n minus m by 10, which is 2788, as we saw before. Okay. Then I'll again repeat this in the next cycle. Remainder, now n mod 10, last digit 8. Okay. Then value changes to the current value of VAL times 10 plus rent. The current value of VAL is 4. So 4 into 10, 40 plus remainder 8 is 48. And then I do the same thing. N is equal to n minus rem by 10, which now extracts the last digit, throws it out, 278. Now I repeat this. Okay, so I repeat this. Remainder is now n mod 10. Last digit of 278 is 4. And now I say value is value times 10 plus rem. Current value is 48. 48 into 10 is 480. 480 plus this last digit 8. So that is 488. Okay. So you see, by multiplying by just 10, we are pushing the digits to the left by one place before adding the new digit. That is the idea. Okay. Multiplying by 10 pushes every digit to the left by one place, and then you add the remainder. And then n is equal to n minus rem by 10. Again, n minus rem is now 270 divided by 10, 27. Let's repeat. Let's complete this. Okay. So I hope you're getting a hang of this, but let's complete this. So remainder is n mod 10. In this case, it is 7 because n is equal to 7. Value is equal to value times 10 plus rem. What is the current value? 488. 488 into 10, 4880 plus 7. 4887. Okay. And then n is equal to n minus rem by 10, which is equal to, throw out another last digit, which is 2. Right? So we are nearing the end because now n has become a single digit number. So now rem is equal to n mod 10, which is equal to 2. Is it? What is it? So we have a special case now. You see? All right. So here's the thing. So we will continue this until the point. Well, okay, we don't need to continue this. N mod 10 will still give you the last digit, which is equal to 2. Just that the quotient will be 0. Okay. So that is all right. Then value is equal to value into 10 plus rem. Current value is 4887. 4887 into 0, 48870 plus 2, 48872. Is that okay? And now is the interesting one. N is equal to n minus rem by 10. What does that give us? N minus rem is now 0. 0 by 10 is 0. So when n becomes 0, we should stop. Right? Because there is nothing more to do. So n has become 0. We should stop. So this sequence of 3 commands we will go on repeating for as long as n is non-zero. Okay, so now let's do this. Write this algorithm. So else case, that is when n is positive, what are we really supposed to do? We are supposed to continue this for as long as n is non-zero. So let me initialize value is equal to 0 first. Okay, and then this is where we use the while condition because for becomes complicated. While n not equal to 0, just continue, right? Rem is equal to rem, sorry, n mod n, val is equal to val into 10 plus rem, right? Value is equal to value plus rem, and then reduce the value of n. N is equal to n minus rem by 10, right? This is all you have to do and end while. Okay, so this completes the algorithm in the case when n is positive. So and if, all right, so this is the algorithm for reversing the number. Okay, so in case, so I would suggest that you again take an example and run this algorithm manually and convince yourself that this works correctly. Okay, is that okay? So that's it. So that's it about these algorithms that I wanted to say. 1 second, let's see if there is something more. Not much more. Okay, so we will stop here and see if there are some more algorithms. We'll see them in the next part. So we'll stop here now.